So now let's quickly take a look at how we get interval estimates for the variance of a normally distributed population based on the sample variance. So here's the scenario. We've got our population. It has some normal distribution. We don't know much about this normal distribution. We want to estimate its variance to get a feeling for what the variance is of this population. And so what do? We grab our sample. We measure the sample variance, which, if you recall, is the sum of the differences between the observations and the sample mean divided by n minus 1, the sample variance. So we measure the sample variance, and then we would like to estimate the variance in the population. So, we might imagine, that maybe n is equal to 10. We take 10 samplings, and we measure s squared is 7, let's say. Okay, so we want to know with n equals 10 and a measured sample variance of 7, how close is that to what can we say about the actual variance in the population? Can we say that it's between such and such? With how much certainty? What can we say? Our goal will be to say we're 95% certain that the variance is between, I don't know, A and B. And the goal is to find what these numbers A and B have to be. Okay? So we want to get some bounds that we can be reasonably sure that the variance is within. Okay, so how do we do that? Well, we know that, that this random variable n minus 1 s squared over sigma squared has, so if I call this thing x, then this is a chi-square variable with 9 degrees of freedom, n minus 1 degrees of freedom, n minus 1. Right. So in this particular example, it looks like chi-squared 9. Excuse me, chi-squared 9. Okay. So this is a chi-square variable with n minus 1 degrees of. Now, just to be clear here, what is this thing that we're looking at, right? So sigma squared is a number. It's an unknown number, but it's just a number. N minus 1. This is just a number. It's just how many samples you took. Capital S squared is a random variable. And I shouldn't have called it x because I was using x up there. Let me call it y. It's a random variable. And its value depends on these measurements that I take. It depends on these measurements and each individual measurement that I took. And it depends on the kind of average value of these measurements, which itself is a random variable. These are all random variables. So it's a random variable that depends on other random variables. And this random variable depends on all these random variables. Okay? These are not numbers, these are random variables. And this random variable y is one whose distribution we know something about. It's this chi-square distribution with n minus 1 degrees of freedom. So now in our situation, n minus 1 is 9, and so we have 9s squared over sigma squared is our particular y, which is a chi-squared with 9 degrees of freedom. Now, let's take a look at a picture of such a thing. It looks something like this. And what we want to do is we want to come up with some region where we're 95% certain our answer lies. And visually what we're going to do is something like the following. We're going to chop it off on either side so that inside of here on each side there's going to be 2.5% on each side, so that 95% is in the middle. We're going to be nice and egalitarian about it. And we're going to say that a chi-square variable, any chi-squared variable, is going to be 95% certain to lie in a region like this. And that's how we're going to come up with our region of 95% certainty, our interval of 95% certainty. All right, so how do we actually do that in practice? So you can see that what we're going to do is we're going to say, well, we want to say the probability that y is less than some particular number that we need to find, less than question mark, is going to be 2.5%. So we have to find what question mark needs to be, and the probability that y is bigger than question mark is 2.5%. And the question is, what are those two y values? So the answer is, this is exactly what the tables are for in the back of a statistics book. So for example, let's suppose we're trying to find this value right here on the x-axis. So in other words, we're trying to say, what is the value, this is going to be this blank, such that a chi-square variable with 9 degrees of freedom, only 2.5% of the time is to the right of that value. Well, this is exactly what the chart is telling us. We look here at 9 degrees of freedom. So this is the chi-square chart. And we see with 9 degrees of freedom, if you want to be 2.5% certain that you're to the right, if there's a probability of 2.5 that you're to the right, how far to the right do you have to go? You have to go out this far, over to 19 or so, right? So what does that say? That says the probability, if I read this chart, the probability, I have the wrong thing here, that y is greater than or equal to 19 is 2.5%. So this value that you need to be, to have alpha certainty that you're bigger than that, alpha probability that you're bigger than that, is called chi squared subscript 0.025 9 degrees of freedom. So by definition, being 19, this is the number such that you have a 0.025% probability of being to the right. So general probability that a chi-squared 9 variable is bigger than this magical number chi-squared 9 alpha comma 9 is alpha. Now how do you do the other interval on the left, or the other endpoint on the left? So to figure out what this number is on the left, you know that 2.5% of the stuff is supposed to be to the left, which means that 97.5% is going to be on the right. So this second question mark is going to be the number such that 97.5% of this stuff is to the right of it. That goes by the name, so the probability that y is bigger than or equal to chi squared 97.59, that's going to be 0.975. So that's the number that we're looking for. And you can see it right on this level here. And the answer is 2.7. So we know that if you look at the value of 2.7, the probability that y is bigger than 2.7 is 0.975, which is to say the probability that y is less than 2.7 is 0.025. So altogether, we know that the probability that y is between these values of, let's see, bigger than 2.7, did I put that right? No, I put that wrong. Right, no, that's right. The probability that y is bigger than 2.7 and less than, what did I get up there, 19, is 95%, right? So those are the two endpoints that I found over here, and 95% of the time my chi-square variable is in between. So then we just read that variable, that stuff off the chart. So in other words, that says the probability that 2.7 is less than 9s squared over sigma squared is less than 19 is 95%. And now we can take these two inequalities separately. 2.7 is less than 9s squared over sigma squared, and 9s squared over sigma squared is less than 19. Sort them out to kind of solve the inequality for sigma squared, and then recombine them, and we'll get some interval estimation for what we know about sigma squared with that same probability. So in other words, this inequality, these two inequalities are these two inequalities, and that's the equivalent information of sigma squared is less than 9s squared over 2.7, and sigma squared is greater than 9s squared over 19. And you put those things together, and you find that this is equal up here to the probability that 9s squared over 19 is less than sigma squared is less than 9s squared over 2.7. So I'm 95% certain when I take my measurement that the population variance is between whatever I read on my sample times 9 divided by 19, or whatever I read on my sample variance times 9 divided by 2.7. So for our particular example, scrolling way up here, we got our sample variance was 7. And scrolling way down here, we find that we are 95% certain that that 9 times, so I squared was 7, times 7 over 19 is less than our variance, is less than 9 times 7 divided by 2.7, which is, I don't know, let's use a little calculator here. Let's see, so 9 times 7 divided by 19, I get a little like 3.3-ish. And for 9.7 divided by 2.7, I got 9 times 7. Okay, 9 times 7. So that's 63 divided by 2.7, 23.3. So that's a pretty wide range. We are, to get 95% certainty, we have to have this pretty wide range that our variance could be between 3.3 and 23.3. So in conclusion, we'd say that 3.3 less than sigma squared less than 23.3 is a 95% confidence interval for sigma squared, the population variance.